right, so what I have going on today is I want to use implicit differentiation to find an equation of the tangent line to the curve at a given point. You notice I didn't call it a function, because when I'm doing implicit differentiation, it's often not a function. And actually, I think this is an ellipse, but it doesn't matter. It's just not a function. You can tell because there's a higher order on the y. It's x squared plus xy plus y squared equals 3. X squared plus xy plus y squared equals 3. And I want to find the tangent line when x is 1. Well, a tangent line requires a point and a slope. Derivative always gives slope. So we're going to have to do a derivative. And if I say at x equals 1, I got to get the point. So if I'm going to start here by finding the point. Okay, we need a point and a slope. The slope's going to come from derivative. I want to finish the point. So if I'm going to find the point, I'm going to have to plug 1 into the original equation to figure out what y is. And I don't want to waste time with that. That is algebra 2. So if I plug in x, the problem here is you get a second order equation with y. Right? You're going to find a y value. So we're going to try to find this. And one of the things I want to make clear at this point is that you come down here and you solve all this, and you have to check your y values in non-functions. Because I'll tell you when you check your y values, you'll find that y equals -2 doesn't work. So my point for this, all right, is 1, 1. So now I have a point from the original function, and now I just need a slope. And if I have to get a slope, I will need a derivative. So I'll get rid of that, add x equals 1, and say, hey, I'm going to do this for a point 1, 1. And again, every time we do this, we're doing it with respect to a variable, dy or dx. So I see x squared, that's 2x dx, plus, guys, the xy term is a product rule. Derivative of x is dx times y, plus x times derivative of y is 1 dy. Those two terms match xy. Then the derivative of y squared is 2y dy, and derivative of 3 is 0. Now I have to get dy dx, right? I have to solve for dy dx. And again, this is more of an algebra exercise than anything else. I'll put all the dy's on the right. So I get 2x dx plus y dx equals negative x dy minus 2y dy. I'll divide all 4 terms by dx. I suppose I could have factored dx and dy. All right, so I did another step here. I factored out the dy dx, and again, I just divide. So I get dy dx, the derivative of that function, x squared plus xy plus y squared, is equivalent to 2x plus y over negative x minus 2y. And not to be lost on us at this point, we've done a lot of work, but really I don't want the derivative. I just want the slope at 0.11. So once you get a derivative, you just have to evaluate it. It has x and y in it because it's not a function. So I evaluate dy dx by using the line and the point at 1, 1. Get 2 plus 1 over negative 1 minus 2. At 3 over negative 3, so I get a slope of -1. And now I can go to the entire page because now I have a slope, -1, and I have a point. Write the equation of the tangent line in point slope form. How about y minus 1 equals -1 times x minus 1, because the point was 1, 1. And again, anytime we're trying to find tangent lines, you need a slope and a point. The slope comes from derivative, the point comes from the original function. All right? Likewise,